today, I have an interest in solving a specific class of problem. Everything that we've discussed thus far has been completely in general, in particular, by definition. I have devised three kinematic quantities: the notion of position, velocity, and acceleration. And I know that mine is a universe of change. The locations of objects change, and so I have displacement. From the displacement, I define the velocity on average and the acceleration on average, and by a judicious application of calculus, I can create those instantaneous quantities. But they apply completely in general. They describe absolutely any object or event that happens in the universe. So what we're going to do today is be more specific and less general and describe a particular set of problems that we have an interest in that are problems where the acceleration is in fact constant. I know that I've defined acceleration as the rate of change of velocity, and I know that acceleration can also change. And we acknowledge those. I think I can repeat them now, that the derivative of the acceleration is the jerk, and then the snap, and then the crackle, and then the pop, and then the lock, and then the drop is the last. Successive derivatives. Well, it turns out there are a great many problems that can be solved where the acceleration is constant or approximately constant. One of the best examples of this is motion under the influence of gravity near the surface of the Earth, where we presume that an object falls with a constant acceleration equal to the acceleration due to gravity. I say presume because that's not at all true. The fact of the matter is that the influence of gravity, or the effect of gravity, as we'll discuss later on in our course, is not in fact constant. Also, I'm discounting the viscous drag interaction between the falling object and the air that it falls through. And so when an object falls under the influence of gravity, the acceleration is not constant, but it's nearly so. It's sufficiently close to constant that it makes a good approximation. And since making approximations sort of eases my solution, physicists are notorious for making approximation. The whole idea of the spherical cow. A cow is in no way spherical, but if you want to treat it as a mathematical object and describe its behavior with respect to physical laws, the joke is that the physicist would say, consider a spherical cow. In approximation, we'll also many times talk about surfaces that are frictionless, which of course is an absurdity. And we do these approximations to ease our way through the calculation. It does not mean that the results are bad. They're perfectly useful results, but they are arrived at more simply, and that's appealing. So what I'm going to consider today, that the acceleration, which I have defined, I don't mean defined two ways, but I have two perspectives on it. The acceleration, which of course is a vector quantity, is the change in the velocity vector divided by the time in which the velocity vector changes on average. That is, A is delta V over delta T. And if I choose, I can treat this as a derivative. The derivative of the velocity with respect to time is the acceleration. But I'm going to presume that the velocity is such that when I take the derivative is constant. That is, the result of the derivative of the velocity with respect to time, the acceleration, is a constant value, a particular number. Now, mathematically, that may land very well in your mind, but I can visualize it as well. Consider this graph. I'm going to propose a graph of what motion with constant acceleration should look like, and I'm going to make a graph of this velocity as a function of time. In principle, the velocity whose rate of change on average I would discover, or that I would take the derivative of. And I'm going to imagine that I start here with some initial velocity v0 that I draw on the vertical axis of my graph. Now, what would motion with constant velocity constant acceleration look like? Well, since the acceleration is the slope of the velocity time graph, my expectation is that this graph would have a constant slope, which means it's a line. In any physical instance where I'm making an approximation of motion with constant acceleration, the velocity time graph will be a straight line. It might be a shallow line, it might be a steep line, it might in fact be a line that has a negative slope in the case where the constant acceleration in question is negative, but it's going to be a line. No matter how exotic the physics is, it's going to be a line. So this is a graph of the velocity as a function of time. And if I describe the velocity on average, consider that there's some final velocity here that I can obtain. That I do obtain somewhere along this line. There's a particular time t at which I have some velocity v. marked here on the horizontal axis is t, and along the vertical axis v. In that interval, there's some average velocity, but because the velocity increases uniformly, that is, the rate of change of the velocity is the same in every instant of change in time. That's a fancy way of saying it has a constant slope. Then it's also okay for me to write here that the velocity on average for this graph, that this graph describes, is the final velocity plus the initial velocity divided by 2. A word of warning, you can't always do that. I can do it here in this instance because of the constant slope. If I was describing a system a little bit more exotic with some varying behavior in the velocity, then this would not be true of the velocity on average. This is how averages work. But I'm going to make use of this during the discussion today, that the average velocity is the sum of the velocities divided by 2. That's how you calculate an average. I have 2 velocities. What is the average? I add them and divide by the number of velocities, which in this case is 2. I want to make an observation about graphs of velocity as a function of time really quick. It's an interesting one, and it's one that we make great use of, not only in this topic of our physics, but going forward in the physics that we do in the future. Consider a much simpler graph of the velocity as a function of time, and I'm going to draw this as simply as I possibly can, where there's a particular velocity that the system has, and it continues with that velocity. That is motion with constant velocity. The slope of this graph is 0, so technically it's motion with constant acceleration. That acceleration happens to be 0. It's motion with constant acceleration, but the acceleration is 0. Here's an interesting observation. If this velocity persists over an amount of time delta t, I might be, it's a little bit mysterious at this instant in time, but I might like to calculate what is the area under this graph. It's a peculiar thing. And when I say area, it's very curious because this is not, this doesn't have, how shall I say it, like a spatial geometry. It is not length times width, but is instead velocity times time, because the height of the graph is some velocity along the vertical axis, and the width of the graph is some interval of time, delta t. Nevertheless, the area that I find under this graph, just right here, area, is equal to this constant velocity that it travels with multiplied by the time interval, delta t, and I realize what this is. By dimensional analysis, I could see that the velocity is meters per second. I multiply by a certain number of seconds. This value of area, which is not area in the geometric, but area in the graphical sense, I suppose we could say, that this area is in fact the displacement delta x. Now, I've done it in the most simple case, but my realization here is that it is true for all graphs of velocity as a function of time, that the area between the graph and the time axis is the displacement. Now, in my example, the area between the graph and the time axis is entirely above the time axis. But imagine, just as an aside, if the velocity graph dipped below the time axis, then I would be evaluating an area that was below the time axis, and I will call that negative area, and it would correspond to negative displacement. And that's not surprising because negative values of velocity multiplied by the positive definite time would result in negative displacement. But that's not my interest for today. We will use this strategy throughout physics, all of our physics, and the next physics, and the next physics, and the engineering, and every technical endeavor. The notion of the area under a graph having some physical meaning, just as the slope does. At any rate, what I would like to do is go back to this original graph. This is a little bit more complicated, slightly more complicated, because the velocity increases as a function of time. And so what I would like to do, just for my interest, is to compute the area under this graph. I would like to compute the area under the graph. So do I know off the top of my head an equation for this area? And I'm going to hash this area out just as I did the other one. It's not going to be as attractive, but I'll put some hash marks in here so we can see exactly what it is, this area that is my area of interest. There's the area that I'm interested in, and I don't know in particular an equation for that area, but I do know that it's a simple trick to divide it up into 2 areas. So I'll take this graph here, and I'll strike a line across it and realize that what I have is a triangle that sits atop a rectangle, and that I can compute the total area. I can compute the total area of the thing. I guess I'll start over here. I can compute the total area as the sum of two areas, the area of the triangle and the area of the rectangle. I'll start with the area of the rectangle. Notice that the height of the rectangle on my graph goes between 0, which is the origin of this velocity time graph here. It goes between 0 and v naught. So the width is v naught, and the length along here is some time interval delta t, or I might just call that interval t, because I know that the t starts at t is equal to 0. So this time interval delta t I could simply write as t. So the area of that rectangle is the height of the rectangle, which is v naught multiplied by t. That is only one of the terms in my equation. I now have to compute the area of the triangle. Well, I do know a formula for the area of a triangle. I'm not completely uneducated. The area of a triangle is 1/2 of the base of the triangle multiplied by the height of the triangle. I have to be careful here because the height of the triangle is not v. If I were to say that the height of the triangle was v, I would discount the fact that the triangle sits atop this rectangle. In fact, the height of the triangle is some change in velocity from v naught to v. So the area of the triangle, I'll write it purely as an area, and then I'll do some algebra associated with it. The area of the triangle is 1/2 the base of the triangle, which is 1/2 of delta t, the base of the triangle, multiplied by the height of the triangle, which is delta v. Now this seems a little bit unremarkable at first blush. This would in fact be the displacement during the time interval displayed on this graph. But I'm going to do a little bit of massaging to it to get something that to our friends who have already had some experience with physics will be very satisfying. Instead of using delta t here, I'll use t. I should have just used t because here I already have t. So that was a mistaken notation, which I'll immediately correct by just calling that times delta. So I'll write this again, appreciating that that is delta x. The displacement is the area. I have no problem at all with v naught times t. That makes me quite happy. But in the second term, I want to replace delta v. And the way that I'll do that is to come back to my equation for acceleration. The acceleration, by definition, is the change in velocity divided by the time. And so the change in velocity, with a little bit of algebraic jiggery-pokery, the change in velocity is the acceleration multiplied by the time. And so what I'll get here is 1/2 the acceleration multiplied by time again, which is time squared. What I've revealed here is an equation that's familiar to those of us who have already done some physics. This is our kinematic equation. It's a relationship among position, velocity, and acceleration, particularly the initial velocity, and time that is not one of my definitions, displacement, velocity, acceleration. It's something new that I've created. It's a new relationship that I might not have guessed at. It is only true in the case where I'm describing motion with constant acceleration. But this equation can be banked and is useful for solving problems in the case of motion with constant acceleration. So here I go, a little feat of algebra. I'm going to start, and I never actually say it, but this is really the work of the theoretical physicist. You can divide physicists into two classes. Experimentalists who work in a laboratory to make measurements and discover phenomena or to verify phenomena. And theoretical physicists who work simply with the ideas of physics in their mathematical forms, combining mathematical forms to create new things. And so the science of physics proceeds really in two ways. The theoretical physicist on a piece of paper describes a thing mathematically that has never been seen before. And then the experimentalist goes into the laboratory and discovers that indeed that happens. Or an experimentalist goes into a laboratory and discovers a thing in nature that has never been seen before. And the theoretical physicist uses all of the known laws to devise a reason why it should be so. It's a rather remarkable interplay, and the whole history of physics is, it could be organized that way, the direction of flow of the discovery of the nature. So I'm going to do a very theoretical thing. And while in my career I've done experimental things, I've worked with experimentalists and I've looked at and analyzed experimental data, my own work has been largely theoretical work. I do my work on paper, and it's up to others to do experiments. So what we do with the derivation is we start from a true thing, much like problem solving, and we proceed with reasonable arguments and careful algebra and see what we discover at the end. So here I go. I'm going to begin with this notion that the velocity on average is equal to the displacement delta x divided by the time in which the displacement happens. For me, that is a fine place to start. A couple of changes I'll make to this equation. I'll say I know delta x. I know that that is the final position minus the initial position. That's by definition. Divided by, I'm not wild about dragging this delta t around everywhere because I know that whenever I begin an experiment in my mind, a thought experiment, Gedanken, I will hit this button on the stopwatch at t is equal to 0 and proceed from there. So for the time in the denominator here, I'll simply write t. Well, a little bit of algebraic rearrangement of this thing, and I'll arrive at my actual jumping off point. I'll multiply the t to the other side of the equation and add v naught over and flip it, such that x is equal to x naught plus v average multiplied by time. That experience right there is very much what I'm talking about when I say you need to be confident with the algebra, otherwise you miss the point of what's going on because you're concentrating on how did he get that t over there, why did the x naught end up where it ended up, and so on. So this is certainly a true thing. And by the way, I love this equation because it predicts the future. It says that if I know the position right now and I know the average rate at which the position changes, I can predict what the position will be at some time in the future. And that's quite remarkable and a thing that we might be very interested in explaining and describing the phenomena that we observe in our universe. But at any rate, I had just made an argument, as a little aside here, I had just made an argument that the velocity on average in the case of motion with constant acceleration, only in the case of motion with constant acceleration, that the velocity on average could be written as the final velocity plus the initial velocity divided by 2. So I'm going to make an algebraic substitution in this equation where I replace the average velocity with this quantity. In a sense, I'm making the equation look worse, and this is a very mild case of making the equation look worse. You want to be careful not to get discouraged if necessity and the rules of algebra cause your expressions to get messier before they get better. It has, I struggled through it as a student, but now it has become a delight to me that I can start a problem that's like this, and then as I go, it explodes and becomes quite large and unwieldy, and then comes back together again to something very small and delicate and very deep, very wee, yes, very wee, but like meaningful. One of my favorite physicists from history is a guy named Paul Dirac. Dirac was one of the early quantum machinists. And he said that if you work from the point of view of getting simplicity in your equations, then you're on a sure line of progress. That's paraphrasing what he actually said. But the idea is a rather remarkable one, that every time that we've engaged nature in this way, we discover that our results are simple. And you say, well, I don't find physics to be terribly simple. Well, anyone can look at physics and say, well, it could be worse. That we find out that our results are usually have a kind of mathematical simplicity. The universe, it's an arrogant thing to say, but the universe actually is not that complicated. We just don't understand it. Well, there's a quote for that. So now I've added this thing in and I want to see where it goes. Well, there are a couple different directions I could go right now. I could do lots of different things, but I'm doing the thing that's going to get me where I want to be. I look here at this equation and I see that I have the final velocity plus the initial velocity. I want to be careful. This v that appears here is not the average velocity. This v that appears here is not the average velocity. This is the velocity at some instant in time. So this v that appears here, v plus v naught, this v that appears here is instantaneous. And I would like to replace it with the instantaneous idea. That does not mean I'm going to inject some calculus. Here's what I will do. Appreciate the fact that the acceleration here presumed constant is the change in the velocity divided by the time in which the velocity changes. That is, a is equal to delta v over delta t. Well, I'll do a little bit of algebra to this as well, this very familiar algebra that I did above here. I'll appreciate, I didn't need to write an arrow there, I could simply write an equal sign, that the change in velocity indeed is the final velocity minus the initial velocity. All change quantities work that way. Divided by, once again, subbing delta t is equal to t. A little bit of algebra to stir this around, and I find that the final velocity is equal to the initial velocity plus the constant acceleration multiplied by the time. Again, an equation that predicts the future. If I know what the velocity is now, and I know the rate at which the velocity is changing, then I can predict what the velocity will be at some later time. At an instant in future time. So once again, I'll make a substitution. I'll take this velocity, v is equal to v naught plus at, and make my equation even worse. So that x is equal to x naught plus substituting v naught plus at and keeping a plus v naught divided by 2 multiplied by t. Just getting worse and worse. Well, I can't let this stand. Sometimes when you're in the middle of your fancy derivation designed to impress, simple things happen, little delightful things that simplify. I have a v naught in the numerator and a v naught in the numerator. That's a v naught plus a v naught. And so I'm content to realize that that's just 2 v naughts plus a times t over 2. It feels like maybe I've turned a corner and my equation is getting simpler. Now in the parenthesis, I have a 2 in the denominator, which of course divides both terms in the numerator. So I have a 2 v naught divided by 2, which will just be v naught. And I have an at divided by 2, which is going to become 1/2 at. Both of these terms should be multiplied by t. And right there, all of the sudden, without warning, I've arrived at my final result. That the final position is equal to the initial position plus the initial velocity times time plus 1/2 the acceleration multiplied by the time squared. That's the equation that I just arrived at from graphical analysis. I've arrived at it again by algebraic manipulation. If we were truly ignorant of what's going on with these things, we might call that verification. But to me, we're a little bit more mathematically sophisticated than that. This is rather obvious. So starting with the average velocity by definition, the thing that I had invented, and mixing all of my definitions together, I've arrived at an expression that I might not have guessed. I've arrived at an expression that I might not have guessed. I know, and some of you know, that there are 3 equations that I'm after. I already have 2. That the final velocity is equal to the initial velocity plus at is an equation that is of sufficient utility that I'm going to keep that one around. I also now have this new expression, x is equal to x naught plus v0t plus 1/2 at squared, that is also a keeper because I will find it to be of great utility in solving problems. That is my first essential derivation that I wanted to share with you today. I'd like to do a second because there is a third equation that I'll find useful when I solve problems. I'm going to begin this second essential derivation from essentially the same point. I had said that the average velocity was the change in velocity with respect to time and solved it around in such a way that I had made the claim that the position, the final position, was equal to the initial position plus the average velocity, which I said was v plus v naught divided by 2 multiplied by t. So I'm starting from this place, which is identical to the previous derivation, but now I'm going to zig instead of zag. I'm going to go off in a different direction. I'm going to do a different thing. This is how I choose to. Appreciating the fact that the acceleration is equal to the change in velocity divided by the change in time, and I apologize that I'm going to be a little bit repetitive here. The acceleration is the change in velocity divided by the time is equal to the final velocity minus the initial velocity divided by time this way. I'm going to do some algebra to this again, but instead of the algebra that I did previously, I'm going to solve it around for time, which is easily done. I'll simply multiply the time to the other side of the equation and divide by the acceleration. On the right-hand side, the time, apparently, is equal to the change in velocity divided by the acceleration. I'll make this substitution in my equation. That is, I'll now say that x is equal to the x naught, which is just going to sit there and spectate. This average velocity v plus v naught divided by 2, the velocity on average, multiplied by, now, v minus v naught divided by a. Again, a sense that I'm making it worse before making it better. A little bit of a sense that I'm making it worse before I'm making it better. Well, I have these 2 fractions that I'm multiplying here, which means I'm going to multiply the denominators, which means I have a factor of 2a in the denominator. It might be illuminating instead to write this as x naught plus 1 over 2a, the quantity v plus v naught, multiplied by the quantity v minus v naught. I didn't have to do that. Some of the things that I do in the middle of these derivations are style, which is why if I were to ask you to do this derivation on a piece of paper, I might find that you take the steps differently or you arrange terms differently. As long as the algebra and the substitutions are correct, that's perfectly lovely. I'm going to subtract this x naught all the way over to the left-hand side of the equation, and I'm going to multiply the 2a to the other side of the equation so that what I have on the left is that 2a x minus x naught is equal to the final velocity plus the initial velocity multiplied by the final velocity minus the initial velocity. On the left-hand side of the equation, I've got x minus x naught, which I recognize as delta x. X minus x naught is delta x, and so for the sleekness of notation, I would like very much to erase that error that I just, if you don't mind. I'd like very much just to write this as delta x. So I'll write this as 2a times delta x, and now the right-hand side of this thing wants to be foiled. It needs to be foiled. You practice enough algebra and things and applying math to sciences, and it starts to feel like there's an insistence that it must happen. You can't leave that be. Foil along with me. V squared minus v naught plus v naught minus v naught squared. The terms in the middle obviously cancel. I have a minus v naught and a plus v naught, and they cancel each other out. These are called the cross terms. Enough experience with algebra, if we were working on a very high level, if this was graduate school of physics, we would not even write the cross terms because it's rather obvious that the cross terms cancel. And it's a delightful thing that the cross terms cancel because it simplifies my equation significantly. With the cross terms gone, 2a times delta x is now equal to v squared minus v naught squared, and I've arrived at my destination. V squared is equal to v naught squared plus 2a times delta x is the third kinematic equation that I claim will be useful for solving problems. Now that's not an equation that you would have guessed. It's not an equation that you would have guessed. It came out of the algebra. I should check, is it dimensionally consistent? Meter squared over second squared, meter squared over second squared, meter squared over second squared. It's dimensionally consistent. I did careful algebra. I had an audience of people watching me. If I had made a mistake, someone would have yelled at me. So this is an appropriate relationship between the kinematic quantities. Again, one that I would not have guessed. The remarkable thing about this, the amazing thing about this, is that as ugly as that equation is, there is a wonderful fact about the nature of the universe that's hiding inside this equation. This equation will appear again in a completely different context. And if we appreciate what's happening in our science of physics, it's actually quite delightful. So there is the second essential derivation that I wanted to show to you. And the payoff, what I get from this, is three kinematic equations. And I think what I'd like to do at this point is write a summary. So I'm going to summarize these things and maybe say a word about them graphically. So in no particular order, the first of my kinematic equations is that x is equal to x naught plus v naught times t plus 1/2 the acceleration multiplied by the time squared. You should have it memorized. For the student of physics, it is automatic. Eventually, you should be able to say it quite fast. X is equal to x naught plus v. We could have a competition. It should be automatic. But it should always be appreciated that the equation is only valid in the case of motion with constant acceleration. How many times are you going to say that, Scheidly? Come on. Every time. Every time. Because we will not fall for any tricks or traps. If I were to make a graph of position as a function of time for any physical system in the case where the acceleration is constant, it would behave this way. At t is equal to 0, it would start at some initial position. I guess I'll call x naught because that's the initial position. At t is equal to 0, it starts at x naught. And then as time goes on, it goes as t plus t squared. It is a parabola. When the acceleration is presumed constant in a physical system, the graph of position as a function of time is parabolic. And this is the simplest, this positive parabola. Of course, it could be negative. That could certainly happen. The parameters could be different. But its behavior is parabolic in the case of motion with constant acceleration. My second kinematic equation, v is equal to v naught plus at, easier to memorize because it's the definition of acceleration. Just spun around to solve for v. With that equation in mind, if I were to draw for any physical system where the acceleration is equal to a constant, if I were to make a graph of velocity as a function of time, that velocity would start out at whatever the initial velocity is and would be linear. Because v is equal to v naught plus at is the equation of a line. V is equal to v naught plus at is in fact the equation of a line. Finally, v squared is equal to v naught squared plus 2a delta x, which I'm just writing for the purpose of summary. These are my three kinematic equations. I don't have a graph to write for this one, but what, in the case of motion with constant acceleration, would the acceleration as a function of time graph look like? Well, this is trivial. It has some acceleration, and that acceleration persists. It is common for students, young students of physics, to be asked about the shape of these graphs in the particular case of motion with constant acceleration. Now, to the problem solving. Problem solving in the context of this special case of motion involves a description of some physical situation. A car is driving down a road, slams on the brakes, there's a tree in the way, or some nonsense like that. And I have to organize all the kinematic quantities in terms of the ones that I know and the ones that I don't know, the ones that are initial and the ones that are final, and then choose the appropriate equation by subbing one equation into the other, come to some conclusion about an unknown kinematic quantity. It's just that simple. Some of you have taken a previous physics course, remember a strategy that was devised for solving problems of this type. Not to get too nostalgic, but we would say that we choose a coordinate, we choose our coordinates, we make a list showing all the quantities that we know, we then choose an equation, solve, and evaluate her accordingly. There's a strategy for it. This is a higher level of physics, so you are free to use whatever strategy that you like to solve a problem. I am perfectly comfortable. On this level of physics, if you simply slap down a true kinematic equation, in the case of a problem that is motion with constant acceleration, and get busy plugging and jugging to find the unknown kinematic quantities.